we have a homework that is due tomorrow night, and that is covering the bonding energy that we had talked about. No, that one covers formal charge. I'm sorry. And then I'm going to do a homework 5 that covers the last couple of sections. And we have a quiz on Friday. The quiz on Friday will cover the bonding energy, a little bit of dot structures, and a little bit of Vsepr theory that we're going to be doing today. And then you need to be starting to read chapter 8. Most of you got your vocabulary assignment for chapter 8 in. We're going to be getting into that on Wednesday. So I said for Friday because we're not going to get real deep into it on Wednesday, but at least look at it before Wednesday and then kind of read it more for comprehension by Friday. Any logistical questions? Okay. I want to go through an example of an energy problem, bond energy problem, similar to what we talked about on Friday. So this is from last year's exam. And you'll notice that I have drawn out the structures here. Now, you know how to draw dot structures, so I could theoretically just say, here's the formulas, but I will generally draw them out for you. Might not draw out water. I'm going to assume you know water, but others I will draw out for you. So it says calculate the enthalpy of the reaction, delta H. Okay, so this is energy, and we're getting that from the bond. Okay. So I need to figure out all the bond energies here. And on the cover of the test, you have a table similar to the one I gave you last Friday. So first I'm gonna figure out what bonds I need. So I've got a carbon-oxygen double bond. And there are 2 of them. Sometimes people will draw a line through it so they remember that they counted both of them. And so then I look at my chart here, and what I'll notice is that for carbon dioxide, this is the one that's a little bit weird. It says 745, but then underneath it says 799 in carbon dioxide. I'm going to go back here and I'm going to say, well, by golly, this is a carbon and 2 oxygens. That's carbon dioxide. So I'm going to have 799 times 2. Okay. Then I'm going to go over here and I'm going to pay attention to the fact that I have 2 ammonia molecules. So while I count 1, 2, 3 of these nitrogen-hydrogen bonds, there's actually 6 of them, right? 2 times 3. So I'm going to come over here. I'm going to see nitrogen-hydrogen, making sure I'm looking at energy, not length, 391. Then I'm going to add all of those up. And these are broken bonds. So they're going to be positive. Requires energy to break bonds. On the flip side, this is nice because I don't have any coefficients. But I got lots and lots of different kinds of bonds. So I've got some of these nitrogen-hydrogen bonds. We already looked that up, and we know that their energy is 391. And I have 1, 2, 3, 4 of these. And it's really easy to lose track of how many bonds there are. Even as I was talking through this with the last class, I said it out loud and didn't write it down. So that's why it's real important to show your work, because if you're showing me you know the steps and you're just making a mistake in counting the number of bonds, then I can give you most of your credit. All right. Notice that we have this carbon-nitrogen bond. And this problem, this is the one that gets overlooked a lot. People will notice the double bond sticking up, but they forget this thing. I have 2 of those carbon-nitrogen bonds. And then notice I have carbon-nitrogen down here, but this is in my multiple bond or double bond. That was a single bond. So I'm going to come up here. The 305 is what I want. Right, so I got both of those. And now I've got the carbon oxygen double bond. Now, when I had the same bond for the nitrogen hydrogen, I just used the same number from the other side. Do I want to use 799? No, because that was our special case. So the carbon oxygen double bond is 745 if it's not in carbon dioxide. So I'm going to use the 745. And there's just one of those. And then I have my water. My water has hydrogen oxygen bond. There are two of them. And when you're looking at this chart, remember that the bond has the same energy regardless of which side I put the atoms on. So if I look over here, I'm going to see, oh, here's the hydrogen, there's no oxygen. Well, that just means I have to look over at the oxygen. So the oxygen hydrogen bond is here. So 467 times 2. And these are formed. So they are negative. And then it's, say again.
Could you go over again how you knew the difference between the two double bond CO2?
Yes. Okay, so if I'm looking here, this is the only one that does this. But it is this unless it's in CO2. So the only way it would be 799 is in CO2. And that specific molecule. So this molecule is obviously not CO2, but I knew to use it in this one. Even though it wasn't written as CO2, I can count the atoms, 1 carbon and 2 oxygen. Okay. All right. So then we add these up. Oh, I can't fit it. Yes, it is. Yeah. This side is positive 3944 kilojoules. I would be careful about doing these problems on your calculator because, I'm not your calculator, your phone's calculator, because a lot of times on the phone, it doesn't follow order of operations. So if you type in 799 times 2 plus 391 times 6, it's going to take the 6 multiplied by everything you already put in, not just the last number. Whereas a calculator that's a dedicated calculator knows the order of operations and will just do by the 391. Alternatively, you can just write the sums of each of these, or the products of each of these. All right, and then on the other side, 391 times 4 plus 305 times 2 plus 745 plus 467 times 2. That's a different number than I got in the last class, so I calculated it the last time. All right, so this is all subtracted off. And we end up with a positive 91. So take this positive number, subtract off this number, and I end up with a positive 91 kilojoules per mole. Okay, and then sometimes I'll ask, is this endothermic or exothermic? Endothermic because it's a positive number. Okay, so stuff we learned last semester, still important this semester. So you can see, this is an acronym. You can see that by the placement of the E, it's not really Vsepr, but that's what most people call it. This stands for valence shell. So we know what the valence shell of an atom is. Electron pair. We have two kinds of pairs that we've talked about. What's one of them? Lone pair. That one we actually call a pair. The other way we have pairs of electrons is with bonds. Okay, valence shell electron pair repulsion. Okay, so when we draw dot structures, I've said this before, I'll say it again, dot structures do not tell us the shape. Okay, it's on a flat surface, there's no way to illustrate well, we don't illustrate the three-dimensional shape on a flat sheet of paper. So don't just look at the Lewis structure and say, this is what the shape is. You have to think about where those electrons are. Now, they're all negative and they want to get away from each other, but they have to stay in pairs. So within a pair, they stay together, but otherwise they push each other away. And so the idea of this theory is we can predict the shape based on how much they repel each other. And then from that shape, we can tell whether or not the molecule is polar. And knowing whether or not the molecule is polar, we can tell a lot about what kinds of things it will do. Will it dissolve in water? Will it dissolve in oil? Will it be reactive in certain ways? So all of those things are tied to the shape of the molecule. That's why we find this important. Okay. So before we get to our shapes, we're going to talk just a little bit about polarity. So our example here is hydrogen fluoride. And we have two kind of drawings of it. One of it has hydrogen as blue and fluorine as green, and one has hydrogen as blue and fluorine as orange. And I had a little video where the orange showed up, but the video doesn't work. So the fluorine is the green. Okay, so in looking at this picture, we've got the electric field off where it says B. That's our upper picture with the gray panels on the side. And you'll notice that these molecules are just kind of pointed in every direction. Okay. But if I turn on the electric field, then the panel on the right becomes positively charged and the panel on the left becomes negatively charged. So that's how we're creating this electric field. The molecules that are inside of that are all going to rotate so that the more electronegative fluorine is pointed towards the positive side and the more electropositive hydrogen is pointed towards the negative side. So when we say a polar molecule, we mean a molecule that's going to do this. It's going to line up in an electric field. Now we know that the bond between hydrogen and fluorine is polar because A, they're different atoms, right? They're different elements, it's going to be a polar bond, but also because fluorine tends to be polar, very polar, no matter what it's bonded to. And so since there's only the two atoms, this has to be a polar molecule. But if I have more than two atoms, we can't just look at whether or not the individual bonds are polar because sometimes they balance each other out. So if we think about something like carbon dioxide has oxygens that are opposite one another, kind of like this. Show you on the screen here. Okay, so while the oxygen is more electronegative and it's pulling the electrons away from the carbon, on one side it's pulling to the right and on one side it's pulling to the left. And in doing that, they balance each other out. It's like a tug of war where each side is equally strong. Okay, so that being the case, we don't always have a polar molecule, even if we have polar bonds. So the shape is going to tell us something important. All right, so how do we know whether a molecule is polar? We're first going to look to see if there are polar bonds. And we're going to look to see if there's asymmetry. Or rather, we'll look to see if there's symmetry, and if there's not, it's probably polar. So remember that anytime I have heteronuclear bonds, that means I have two different elements. That's going to be a polar bond. Now, how polar it is depends on the difference in electronegativity, which depends on how far apart they are on the periodic table. In contrast, if I have the same element, those bonds don't have a difference in electronegativity. They're nonpolar. And so if they're all the same element, I tend to have a nonpolar molecule. So all of our diatomics, O2, N2, H2, even F2, all of those are nonpolar molecules because they have the same element. They're homonuclear. And then we've seen the exception with carbon dioxide, that if I have an identical polar bond, such as the carbon-oxygen double bond, if I have identical polar bonds opposite one another, those polar bonds are going to cancel each other out. And when that happens, we have a non-polar molecule. Now, this last one is going to make some more sense as we go through our different shapes for Vsepr theory. But we're going to be talking about the bond angle. So this is the angle that is created by going from one atom to the central atom to another atom. So remember, with a bond angle from geometry, you usually describe it with 3 points, the angle of ABC or whatever. So we have to have two bonds and look at the angle between those bonds. If they are exact, and you'll know what that means in a minute, this is going to be a nonpolar molecule. I guess I didn't actually write that on, but nonpolar molecules usually have exact bond lengths. Polar molecules are going to have something that is less than the ideal. All right, does anybody still need this slide? Okay, so what I want you to do is you're gonna, I think you have one large styrofoam ball and lots of little ones. One of the people at your table is going to take one of the large styrofoam balls and two of the smaller ones. And these sticks are going to represent either the bonds or the lone pairs. Either way, they're electron pairs. You're going to get those electron pairs as far away from one another as possible. So your first bond that you form is just kind of arbitrary, right? Doesn't matter where you put that. Where can you put this other bond so that it is as far away as possible? I get that in there from the original. All right, so did everybody come up with something that looks like this? Yeah, that one's pretty intuitive. Okay, not too hard. Okay, so we can see on this slide representations of this. And we're going to put this into the chart that I handed out to you. But it's got some information on here. We're going to divide up the information into the class, and I'll talk about what that means in a minute, and the shape. So the shape is the molecular shape, what the molecule looks like. The class is the electronic shape. And we're going to describe the bond angle. So what's the angle of a straight line? 180 degrees. And we keep things simple in this case. This is a straight line, so we call it linear. All right. So I'm going to switch over to our chart. Where is it? Okay. So I lost my pen. In our top row here, I'm going to point out some things. First of all, if you turn the paper over, on the back, it gives you some alternative names for things. This is a theory that we have lots of different names for things. So I talked about the electronic geometry. Some people call it the class. Some people call it the electronic region geometry. This means we include lone pairs, LP, and bonds. The molecular geometry, or the molecular structure, or the molecular shape, those all mean the same thing. That means, what does the molecule look like if we can't see the electrons? The electrons are still influencing the shape, but what do the atoms look like in their particular arrangement? And then we're going to be looking at regions of electron density. This is what determines the class. Your book calls this the steric number, and it is bonds plus lone pairs. All right. So we just looked at an example where we had two atoms attached to the outside or to the central atom. So on the left, the A stands for our central atom, and the X stands for the atoms that are attached to it. We don't know what these atoms are. They could be anything. But a good example of this is one we've already talked about, carbon dioxide. So we know that that carbon has oxygens to either side, and it has no lone pairs. So our regions of electron density here, we're going to plug in a 2, because I have this region here and I have this region here. So even though they're double bonds, remember those double bonds can't get away from each other, because if I pull apart the double bond, the atom's going to go with one of them and not the other. So that doesn't happen. Okay, in order to be a double bond, those have to stay together. So they're just 2 regions, and that's going to be the sum of the bonding regions and the non-bonding regions. So I'm going to put up here the class. Sorry, not the class, the steric number is equal to bonding regions plus lone pairs. All right, and we said this was called linear, and the bond angle was 180. And the shape of the molecule is also linear. Okay, since there are no lone pairs on the central atom, and all we care about as far as lone pairs are concerned is the central atom. Okay, so no lone pairs on the central atom means that I have an identical class or electronic geometry and a molecular shape. All right, so now we're going to add a third atom to our structure. And remember, we want all of them to get as far away as possible. So if you need to move one of your original bonds, you can do that. All right, so you may have ended up with something like this. If it looks like a T, it looks like this. You've got these atoms that are on the sides a little bit too close to that bottom one. You can spread it out a little bit more. If you had something that kind of puckers up, again, you're getting the bonds closer to each other on one side. They can spread out a little bit more by being on the other side. Okay, so this shape kind of looks like a triangle, and it's all in one plane. So we're going to call this trigonal planar. And a good example of that would be, oh, what did I use last time? BH3, one of our electron deficient ones. Or we could use something like the carbonate ion that we had on our quiz, where the central carbon didn't have any lone pairs and it was resonant, right? So all of those bonds are really equivalent to one another at 1 1/3. So that would also qualify. I'm gonna write that out. All right, so our steric number or our regions of electron density is just the sum of the next two boxes. And the bond angle is going to be 120 degrees. And in this example, we have the same, we have no lone pairs, so the same geometry is there for the electronic geometry as is for the shape. Now, if we take the ball off of one of these, that toothpick without anything on it, that's going to be our lone pair. Okay. If I am looking at this shape, but I can't really see the lone pair, electrons are really small and they move really fast, all I can see are the atoms. I'm not going to describe this as trigonoplanar anymore. This is what I would call bent. Okay, sometimes you'll see V-shaped, but this is bent. Okay, so a good example of this is ozone. Ozone has two oxygens, one of them double bonded, one of them single bonded, shows some resonance there. And that central oxygen has a lone pair. Remember, when we're counting lone pairs for Vsepr theory, all we care about is that central atom. So the central atom has one lone pair and two bonded atoms. So it still has a steric number of 3, which means this is still in the same class. So our electronic geometry is still trigonal planar. But the shape of the molecule is a bent molecule, not trigonal planar. Okay, so what happens to the angle? This is where what I said about exact bond angles comes in. The lone pair doesn't have an atom attached to it, a nucleus attached to it. So it is more negative. It is pushier, more repulsive. And so it's going to push on the other bonds more than the bonds are going to push on each other. And so these two bonds actually get a little closer to one another. And instead of this being 120 degrees, it's going to be something less than that. All right. Now, how much less depends on the molecule. Might be 119.5, might be 116, 115, so it can change quite a bit. But this less than sign is an indication that this is a polar molecule. All right, so now I want you to try and do 4. This is where it gets a little bit tricky. hold up your molecules so I can see them. All right, and I'm getting about an equal mix. So that is what I expect. So some of you have a molecule that lays flat like this. And so we have basically 90-degree angles. Okay, but this is where you need to remember that we're not dealing with two-dimensional space, we're dealing with three-dimensional space. And these electrons really want to get away from one another. So our structure that is more like a little tripod, that is the more correct structure. This allows the atoms a little bit more space, and this bond angle is a little bit more than 90 degrees. Okay. So this shape is called a tetrahedron. Good example of this is methane. And this might not be obvious, but this is a non-polar molecule. Okay, so we don't have atoms exactly opposite one another. But if we think about this being like a tripod with the three atoms kind of resting on the bottom and one pulling straight up, the amount that this pulls straight up is balanced by these three that pull a little bit down. So they're each pulling down with about 1/3 of the strength of the one pulling up. So 3 times a third balances it out. And that works in every direction. So that's a non-polar molecule. All right, I'm going to write down real quickly the last 2 examples. Ammonia has 1 lone pair on the nitrogen, and water has 2 lone pairs on the oxygen. They both are in that same class, have the same scalar number of 4, but they have lone pairs. So if I take one of the atoms off of the top of my little tripod, so now I just have a lone pair at the top of the little tripod. Now I don't really have a tetrahedron anymore. I have kind of a pyramid. It's triangular in shape, but it's a pyramid. So instead of trigonal planar, we're going to call it trigonal pyramidal. Some people say pyramidal, that's fine. Oops, wrong box. And again, this angle is going to be less than 109. So for ammonia, I think it's around 106. And then for water, it's also less than 109, but it's closer to 104.5. When I take away 2 of these atoms, I am back to that bent shape that I had before. So again, I just call this bent. As far as the electronic geometry, since I'm in the same class, all of these are considered tetrahedral electronic geometry. Okay, these are the most important shapes. We will briefly go over the other shapes on Wednesday, but these are the most important ones because those are the ones that you're going to most commonly see, particularly if you take organic chemistry. All right. Questions?